Both stepper motors are brushless. They consist of a permanent magnet rotor and coil stator. Let's look at a simplified model. The motor stator has two wires. These are wrapped around an iron core. Current flows from A1 to A2. A magnetic field is generated. One end is S and the other is N. When current reverses, the magnetic field reverses. This applies to wire B as well. Now we add a permanent magnet rotor. Current from A2 to A1 is passed. The rotor rotates 90 degrees. It rotates under the magnetic field's attraction. The rotor remains there. Next, disconnect the current from wire A. Pass current from B1 to B2. The rotor rotates 90 degrees again. Current from A1 to A2 is passed. Current from B2 to B1 is also passed. We can control the rotor's 90-degree rotation, while keeping current from B2 to B1. Pass current from A2 to A1. The rotor is now affected by two magnetic fields. It rotates 45 degrees. We can control the rotor to rotate 45 degrees. This is achieved with single-wire energization. The execution order and duration change direction. The rotor's speed can also be adjusted. This is a basic bidirectional stepper motor. Each electrical signal makes the rotor rotate. The step angle is 45 degrees. This is too large for precise control. Let's reduce the step angle. We double the four windings. These are wound with two wires. The generated magnetic fields oppose each other. The rotor poles are also doubled. Sending signals in the same order changes the angle. The new step angle becomes 22.5 degrees. For smaller step angles, we could double windings. This is theoretically valid. However, it's not necessary. To achieve smaller step angles, the 42-stepper motor uses clever designs. The rotor has a permanent magnet with one pole. Assume this is the N pole. This magnet has 50 teeth. A 50-tooth internal gear is designed. It corresponds 1-to-1 with rotor teeth. 2 teeth are removed. The remaining 48 teeth divide into 8 intervals. Each interval is 1.8 degrees. Teeth number 1 and number 5 are opposite. Teeth number 2, 4, 6, and 8 are 1.8 degrees apart. Teeth number 3 and 7 are 3.6 degrees apart. These teeth replace the stator core's arc shape. We obtain a modified stepper motor. The step angle reduces from 22.5 degrees to 1.8 degrees. Only 4 electrical signals are needed. Power on in the order A1 to A2. Then B2 to B1. Next A2 to A1. Finally B1 to B2. Each electrical signal moves the rotor 1.8 degrees. The rotor aligns with the winding core's teeth. To increase torque and stability, another permanent magnet is added. This magnet has an S-grade outer ring. The two permanent magnets' teeth differ by 3.6 degrees. They are staggered. When powered, the S-pole attracts the front magnet. The N-pole attracts the back magnet. This structure provides greater torque and stability. This is the principle of the 42B stepper motor. Now let's examine the 28BY J48 stepper motor. It uses a different design. Recall the earlier question. The 4-winding stator had a fixed rotor angle of 45 degrees. The 8-winding stator had 22.5 degrees. The 16-winding stator had 11.25 degrees. The 32-winding stator had 5.625 degrees. The 28BY J stepper motor has 32 windings inside. But it has only 2 sets of coils. It employs a clever design. One set of coils is clamped by magnetic sheets. This set has 8 claws. It consists of 2 coils A1 and A2. They share a common positive power supply. When A1 is on, a positive magnetic field forms. The rear magnetic sheet's claws gather. The magnetic flux lines become N level. The front sheet's claws become S level. When A2 is on, the magnetic field reverses. The poles of both sheets change. The same applies to the second coil set. When both sets of coils operate together, the 4 coils share a power supply pole. The claws of the magnetic sheets stagger. There is an 11.25 degree difference. This simulates a stator with 32 windings. The rotor has 8 pairs of N and S poles. This gives a step angle of 5.625 degrees. A 1:64 reduction gear is added. The actual step angle is 5.62564. This equals approximately 0.0879 degrees. When two sets of coils superimpose, the four coils share a power supply. The magnetic claws interlace. There is an 11.25-degree phase difference. This simulates a stator with 32 windings. The rotor has 8 NS-level pairs. This results in a step angle of 5.625 degrees. Adding a 1 to 64 gear, the actual step angle becomes 0.0879 degrees. This design provides precise control. The clever mechanism enhances performance. The 28BYJ motor achieves remarkable efficiency. It's suitable for various applications. Both motors have unique advantages. They showcase innovative engineering. Precision control is paramount. Each motor operates efficiently. They serve different needs in automation. Understanding their mechanics is crucial. These designs reflect advanced technology. They illustrate the evolution of stepper motors.